Today we're going to be talking about polynomial functions and modeling, putting them into application into word problems. So we're going to be, first of all, defining what is a polynomial function. And we can see that here we have a polynomial function where n, which will end up to be our exponent that we will see, needs to be a non-negative integer, meaning it needs to be positive and it needs to be a whole number. And so we go through and we see that the function given by this representation here is a polynomial function of degree n. And just a reminder that the degree is our largest exponent. So if we want to know what is the degree of a function, we just look for the largest exponent and we can say then that is a polynomial of degree 4 if 4 was the largest exponent. We know the leading coefficient to be a, and we know that the polynomial functions have to have positive integer exponents. That's exactly what we had said previously above. And so it cannot be negative and it cannot be a fraction, is basically how you can say that. The domain of all polynomial functions is all real numbers, which means that the function cannot have any restrictions. So we will say no restrictions, and that goes back when we were looking at section 1.2 and looking at restrictions that it cannot have 0 in the denominator and we cannot have a negative under the radical, and the same applies here in the polynomial function. So we've got 4 examples here, and we're going to determine whether or not these are polynomial functions. The first, we have 4x cubed minus 5x minus 2. We see that we have 2 exponents. One is a 3 and the other is 1. Neither one are negative and they both are whole numbers. So we can say yes, this is a polynomial function of degree 3 with a leading coefficient of 4. And the leading coefficient that we pull out is the coefficient of the highest degree, or the highest exponent. B, 6x to the negative 4th plus 7. We see that we have a negative exponent, so therefore that immediately takes it out. It is not a polynomial function. C, we have a square root, and so automatically we see that we do have a restriction on C, and so we can say that no, that is not a polynomial function because it has a radical. And D, we have 15x squared minus 2x to the 4th. We want to write this in standard form to where it is in decreasing order of exponents. So we can rewrite that as negative 2x to the 4th plus 15x squared. Both of those exponents are positive, and both of those exponents are whole numbers. So yes, D is a polynomial function with degree 4 and leading coefficient of negative 2. Now we're going to look at polynomial functions of no or a low degree. So we have 4 different functions here. We have the zero function, a constant function, the linear function, and the quadratic function. A zero function is exactly what it is. It's a function that is equal to 0. There is no degree because there is absolutely no x. And so it's just a function that is equal to 0. We will not be doing too much with that zero function. Then we have a constant function where it is just a constant. So for instance, we could have f of x equals 3. That would be the constant function. The degree would be 0 because it would be as if fx was not fx, but x is raised to the 0 power. For we know that anything raised to the 0 power is 1. So in essence, we could write that as f of x equals 3 x to the 0 power. And since we know that to be 1, it's the same thing as saying f of x equals 3. We have a linear function that we may be a little bit more familiar with, where it's y equals mx plus b. In this case, we've got f of x, which is our function notation, equals a, our leading coefficient, x plus b. Same situation. And we have a degree of 1. Quadratic function, another familiar one for us, ax squared plus bx plus c, and again we have a degree of 2. So now what we want to do is we want to write some equations for the linear function f such that f of negative 1 equals 2 and f of 2 equals 3. This is just written in a little bit fancier way than what we know. We normally have points written in terms of coordinates of x and y. This is written in function notation, but we know that the x value is what's inside of our parenthesis. It's typically written as f of x equals y, so we can pull out our x and y knowing that notation. So we have a point of negative 1, 2, and we have a point of 2, 3. That's x, that's y, that's x, and that is y. So there's our 2 points, and we want to write it in linear function, so therefore we want it to be in the form of y equals mx plus b, or we could say f of x equals a times x plus b if we want to write it as we see it above. And we want to determine our slope. Going back to what we have learned, probably Algebra 1 maybe, y2 minus y1 over x2 minus x1, that is slope. We represent slope with an m. And so it doesn't really matter which is our y2 or our y1, but as long as whatever's our y2 needs to be our x2. So if I take my slope and I say y2 minus y1, so I'm taking 2 minus 3, divided by x2 minus x1, so negative 1 minus 2. I work that out as 2 minus 3 is negative 1, and negative 1 minus 2 is negative 3. Both negatives make a positive, so my slope is now 1/3. So I want to write the equation in the form y equals mx plus b given these 2 points. So the first thing I had to do was find slope, so I've got my m. Now I'm left to find my b. I can use either point I want to fill in for my x and my y. So I'll just use the first point that's given. So I have 2 equals my slope, which is 1/3, times x, which is negative 1, and I'm solving for b. Multiplying that out, I get 2 equals negative 1/3 plus b. I'm solving for b, so I add 1/3 to both sides. So I get 2 and 1/3 is equal to b. It is really not proper to leave your y-intercept, which is b, as a mixed number. So we're going to go ahead and make it into an improper fraction. So it's not proper to be proper, it's proper to be improper. How about that? 3 times 2 plus 1 leaves me with 7/3 as my b value. So the final result of my equation is y equals 1/3 the slope times x plus 7/3, which is my y-intercept. And that is my equation of a line given 2 points. And so down below we see a different terminology for slope. It's called average rate of change. And that means nothing more, and you can see it down here, that average rate of change is slope, which is the same thing as m, which is the same thing as rise over run, same thing as change in y over change in x, and same thing as delta y over delta x. And the triangle in Greek does mean change, and we call that the delta. And so that's what that means, and that's just a different way in which to write slope, all these different ways. And so we saw up above that we had f of b minus f of a all over b over a. And so this is the same notation as we saw above, okay? Now, with slope, you can have an average rate of change or you can have a constant rate of change. We see the constant rate of change in a linear function because when you go to graph a line, your slope stays the same. So if my slope, as we saw here, is 1/3, no matter where I was on the graph, I'd be going up 1 over 3, up 1 over 3. But that's not the case with every graph. We could have an average rate of change of 1/3, but with the linear function, we have the constant rate of change that we see. And we always know that our slope can never be 0. It has to be a non-zero average rate of change for that slope. So as we flip over to the other side, we have some characteristics of linear functions that we want to talk about. And we're going to talk about them verbally, algebraically, graphically, and analytically. So verbally, we can say of a linear function that it is a polynomial of degree 1. Algebraically, we can say that it's f of x equals mx plus b. Again, more familiar, y equals mx plus b, same thing. Graphically, we know that it is a slant line. Notice that that's a slant line. We do not have a vertical or a horizontal line, because it has to be a slope that is greater than 0 or less than 0. It cannot be 0, and it has to have a slope, because a vertical line would have an undefined slope. A horizontal line, and look at that, I wrote vertical twice. A horizontal line would have a slope of 0, and so neither one of those would be a true definition of a linear function. Analytically, we would say that it's a function with a constant. There's the non-zero, again, rate of change, which we know of as slope. F is increasing if the slope is greater than 0. It is decreasing if the slope is less than 0. And it does have an initial value of b, and we know that to be where the graph crosses the y-axis, so we call that the y-intercept right there. So that's our characteristics of a linear function. Now we're going to move into a quadratic function, and we've got a couple pictures here of a quadratic function. We've got a quadratic function that is that makes the shape of a parabola, and the one here on the left is when a, our leading coefficient, is greater than 0. And we see that that is a graph that is upward. And then we have a graph of a parabola when a is negative. And we say that if it's a negative, it's a frown. It goes down. But if it's a positive, it goes up. We have several different types of forms of quadratic functions. We have ax squared plus bx plus c. We know that to be our standard form that we can pull out the y-intercept, which is c. And then we also have what's called the vertex form of a quadratic function. And in vertex form, we can actually pull out the vertex, and that's exactly what is described here. The graph of f is a parabola, like we were seeing up there, and it has a vertex of hk. And so inside the parenthesis, we would take the opposite of h and k to get us the vertex. And then we have an axis of symmetry of that vertex that is always our h value, which is, or you could say the x value, where h is equal to find the vertex, we would take opposite of b over 2 times a. And that gives us the x value of the vertex. So if we said the vertex was xy, hence hk, then to find the vertex, we would take the opposite of b over 2a if we were in standard form. And so what we're going to do now is we're going to actually give some, do some work with some quadratics down below, and then we're going to work up to a couple of the application problems. And so here we have a quadratic that is in vertex form, and we want to know what are the transformations that took place from the parent function of x squared into this vertex form here. We see the 2 out in front, and we remember from last section that that represents a vertical stretch by a factor of 2. Okay, that's what the 2 out in front represents. Vertical stretch by a factor of 2. Inside the parentheses, I have a translation to the right by 2 units. And then I have a translation up of 3 units. And that would be the different translations that took place from the parent function to that vertex form. Next, we have 2 different functions that are in standard form, and we're going to then rewrite them into vertex form. First thing we're going to do is get it into representing a as 2, b is -8, and c is 11. To get it into vertex form, I need the vertex, and so I will be looking for the vertex in each one of these. And to find the vertex, we know that to be the opposite of b over 2 times a for my x value. And then when I find my x, I plug that back in to find my y. So we start out with x equals opposite of 8, so that becomes a positive 8 over 2 times a. So 8 divided by 4 is 2. I plug that back into the original equation, and I get 2 squared is 4, times 2 is 8. We'll come up here. 8 times 2 is 16, so that's 8 minus 16 plus 11. 8 minus 16 is negative 8. Negative 8 plus 11 leaves me with 3. So I have a vertex of 2, 3. Now it says I want to write this quadratic in vertex form. So it's y equals a. I can pull the a off of the standard form because it's the same graph, just written in a different form. So 2 times x minus the opposite of whatever x is, which would be h. So 2 squared plus 3. And so that is my equation in vertex form. Now I can do the same thing here with the second graph, the second equation, knowing that a is negative 2, b is 7, and c is negative 3. Making sure I'm still in the screen. And so again, I need to find my vertex, so I take x equals the opposite of b, which is negative 7, over 2 times a, which is negative 2. So it leaves me with 7/4. Not as clean and nice and neat as my 2 is over here, but that's all right. So I get y equals negative 2 times 7/4 quantity squared plus 7 times 7/4 plus 3. And that would be a minus. And then I'll continue my work up here. So that becomes 7/4 squared is 49/16 divided by negative 2, or times negative 2. So I get a negative 49/8. This becomes 49/4. If I want a common denominator, I'll just turn that into 98/8 by multiplying by 2, numerator and denominator. And my minus 3, I want that to be 8, so that would be negative 24/8. Combining my numerators, I end up with a positive 25/8, and remember that is my y value. So my vertex is 7/4 and 25/8. So writing that in my vertex form, I get y equals, my a is negative 2, x minus 7/4 quantity squared plus 25/8. Now, could you have done all of that on your calculator? Absolutely. It's always good to stretch your brain a little bit, doing a little bit in your head, but absolutely. Do not leave these as decimals, though. You would, after you got the decimal, you would convert that over into a fraction. So now we want to write an equation for the quadratic function whose graph contains the given. So here it is, given the vertex is 1, 3 with a point 0, 5. So this one's a little bit easier because my vertex is already given, but I don't know my a, so I need to find a. So my point here, this is my h, that's my k, this is my x, and that is my y. So using the vertex form, y equals a times x minus h quantity squared plus k, that's coming from the equation that we found up here, I'm going to get 5 equals, I don't know a, x is 0, h is 1, so I take the opposite, so it becomes minus 1 quantity squared plus k, which is 3. So I get 5 equals negative 1 squared a plus 3. And negative 1 squared is 1, so I get 5 equals 1a plus 3. Subtract 3 from both sides, so 2 equals a. And now I substitute that back in, so y equals 2 times x minus 1 quantity squared plus 3 to find my vertex, given a point and the vertex.